All right, guys, here is the lecture for scientific notation. I strongly encourage you to use your calculator. If you don't have a calculator, you want to go to desmos.com. Let me share my screen. All right, so here's a Desmos scientific calculator. What you want to do is you just type in desmos.com. It'll take you here, and you'll have this tab called Math Tools. Sorry. You'll have this tab called Math Tools. Graphing calculator will help you in future units when we have to graph. So if you have 5x minus 14y equals 24, it will graph it for you. It'll give you the x-axis and the y-axis of that. It's an easier screen to look at than a small graphing calculator. So that's desmos.com/calculator, but desmos.com and then scientific calculator is going to help you a lot with fractions, really. So if I had 85 divided by 2, right? We know that the division bar is the fraction bar. It'll give you your answer in decimal, but you can also press this button, convert to fraction. And so you can always make sure that your fraction is in lowest terms. So like if I had instead 3 divided by 9, right? That's 0.333. But is that in lowest terms? Or if they're asking you for that fraction in lowest terms, you hit convert to fraction. 3/9 is actually 1/3, because if we think about it, you can divide 9 by 3. So 3 times 1 on the top divided by 3 times 3 on the bottom. You can cancel out those 3's, right? Sorry. So that's like saying 1 times 3 up here, and 9 is actually 3 times 3. So that second set of 3's cancels out, and 3 divided by 9 is equal to 1 divided by 3. So it'll always put your fraction in lowest terms. I know that's not what we're doing today, because today we're doing scientific notation, but this will do scientific notation for you as well. All right, back to this screen. Make sure it's focused enough. I know it's not perfect, but so scientific notation just has to do with exponents, because the form that it is written in, scientific notation means you have a number that's usually a decimal, and it's only going to be one digit in front of that decimal point, and then however many there might be after the decimal point, being multiplied by 10 to the power of something. Okay, that's what we mean by scientific notation. So you're going to take a really big number and you're going to notate it as a single digit. So instead of 671, it'll be 6.71667 times 10 to the power of 2. Good. So because we are talking about exponents in terms of 10 to an exponent, we're going to review the product rule for exponents. And the product rule for exponents is just when I have two terms with this, or sorry, terms, both exponents, and they both have the same base, we can combine them using the exponent rules. So x to the power of a times x to the power of b is actually equal to x to the power of a plus b. So I can add those bases together. So if I had x to the power of 10 times x to the power of 5, that would be equal to x to the power of 10 plus 5, or x to the power of 15. Again, we can go to Desmos and look at why this, or sorry, just show that this is true. So if I have 5 to the power of, let's pick a little low one, right? 5 to the power of 5 is 3,125. 5 to the power of 2 times, remember, 5 to the power of 3, that gives us the same. It's like adding the 2 and the 3 to get the 5, the same answer. Good, so that's the product rule for exponents. The quotient rule for exponents is similar. So if I have 5 to the power of 3 divided by 5 to the power of 2, it's equal to 5. And that's the same as 5 to the power of 1, right? So the quotient rule for exponents is that 5 to the power of 3 divided by 5 to the power of 2 is equal to 5 to the power of 3 minus 2, if that makes sense. So 5 to the power of 3 minus 2, because we're taking that 3 and that dividing it by that second. So that rule is the base to the power of A divided by the base to the power of B is equal to that base to the power of the top one minus the bottom one, right? So x to the power of 8 divided by x to the power of 3 is going to be equal to x to the power of 8 minus 3, which would just be x to the 5th. Okay? And we'll use, let me show you that again. So x to the power of 8 divided by x to the power of 3, but we'll just change x to 5. Let's change it to 4 so that it's a little different. So it was 4 to the power of 8 divided by 4 to the power of 3. And the base can be anything. It just has to be the same base, right? It's 1024. And then if we just have 4 to the power of 8 minus 3, that's going to give us the same answer. And what is 8 minus 3? It is 5. Good. So those are our product rule for exponents and our quotient rule for exponents, which is how we will understand the tools we will use to express scientific notation. Back to this. The general format of a number in scientific notation is one number in front of the decimal, every other part of the number behind the decimal being multiplied by 10 to the power of a variable, okay? If it's a really big number, which is why scientific notation was made, to show really, really big numbers more easily, or really, really small numbers. If it's a big number, that exponent, that n, is going to be a positive, right? So that would be 7.432 times 10 to the positive 5, right? That's a really big number because we're going to move backwards. A small decimal number, 7.432 times 10 to the negative 5. Okay, so the only difference here is that that's a positive exponent and that's a negative exponent. Good. Let's look at these in Desmos. So we said 7.432 times 10 to the power of 5 gives us a really big number, right? And you can even make that 5 bigger. What if it was the power of 7, right? 8, 9. Oops, they doesn't go back 9, right? So the power of 8 means we're making that number, multiplying it by 10 to the power of 8. Because what is 10 to the power of 8? It's a really big number. Good. And then if we take that same 7.432 times 10 to the power of, instead of 5, we're going to say negative 5. Negative 3. So negative 3, instead of 7.432, or instead of a really big number, we're moving it behind the decimal point. We're moving it further back, so it's becoming smaller with each negative exponent. Good. So 7.432 times 10 is just 74.32. Times 10 to the negative first is 0.7432. Negative 2, 0.07432. So you can see that with each increase in the negative exponent, the whole number just moves back or to the right one space. And we put another 0 in front of that number. Good. 7.432 times 10 to the second, right? That number got bigger, second to the third, that number got bigger, that number got bigger, that number got bigger, 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 right? Okay, so that's the difference. If it's a negative number, we're going to look, sorry, if the exponent is a negative number, the whole answer is going to be small. If the exponent is a positive number, that whole number, the answer is going to be bigger, okay? And I'm going to go back to our paper. That exponent is the number of places you move the decimal point, okay? So if we wanted to write 3.127 in scientific notation, let's look at scientific notation. A point B, 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 and the B's can go on, okay? The important point is one number in front of the decimal. Right now, where is the decimal? We don't have a decimal, we have a comma. Our decimal is always after the last number if we cannot see it, right? For number 6, we can see the decimal, it's right here. But if there's no decimal, it just means we put it at the end, right? $3,127, for example. Okay, so this number, 3,127, is not huge, but they are asking us to put it in scientific notation. So instead of 3,000, I just want it to be the number 3. My decimal point is right here. The n is going to be the number of places you have to move the decimal point. So I know it's going to be 3 point, right? And then you have to include all the numbers behind the 3. 127. 3.127 times 10, right? Large numbers have a positive exponent, so that's not going to be a negative exponent. This is going to be a positive. Because small numbers, like this one, have a negative exponent. Good. It's going to be a big number, so that's going to be a positive. And how do we decide what number it is? You could kind of just go to your calculator, right? And just start typing it in. Type in what you know. I know I had to put the 3 in front of the decimal and everything else behind it. And I need to multiply it by 10. Well, that's not what they gave me, right? They gave me the number 3,127. So the number I'm working with is 3,127. Oops. And 27. Good. And right now I have 3.127. Not comma. 3.127 times 10 to something, right? It's not just going to be 10 because that would just give us 31 to the power of 1. Nope, that's the same as just 10. To the power of 2. Nope, that's 300. To the power of 3. That's the number I want, right? So I know my answer is 3.127 times 10 to the power of 3. Why? Because we moved the decimal point from right here to right here. We moved the decimal point 1, 2, 3 times. We move the decimal point 3 times. If it's a big number, it stays positive. If it started as a small number, we make that 3 a negative, okay? How many times do we have to move it to get from this behind the 7 to behind the 3? From behind the 7 to behind the 3, we had to move it 1, 2, 3 times. Good? All right, our next example, sorry, 1 second. Our next example is 86,000. We want to write that number in scientific notation. Welcome to use a calculator if you want. But we know it's a big number. The decimal goes at the end because it wasn't showing up, right? And instead of 86,000, I need one number in front of the decimal. So my one number in front of the decimal is going to be that first number, that 8 point, right? Point and then everything else behind it. You don't even need the zeros, right? Because a 0 behind the decimal is kind of the same as a 0 in front of the 8. If I was just to put a 0 in front of the 8, it doesn't change the value of the 8, right? That's still 86,000. Still 86,000, right? Still 86,000. Just like if I put a 0 back here, that's still 0.000313. So you don't need to include those other ones. You can just call it 8.6, okay? In scientific notation, 86,000 becomes 8.6 times, right? Times 10 the power of something. What is that something? That something is how many spaces did we have to move to get from here to right here where we decided we needed to be? Okay. We moved it 1, 2, 3, 4 times. 1, 2, 3, 4. 4 jumps means it's 8.6 times 10 to the 4th. You're welcome to check that in your calculator. 8.6 times 10 to the 4th, 86,000. Good. Moving on to number 6, this is our first small number. What do we know about small decimal numbers? They're going to have a negative exponent. So I have 0.000313. In scientific notation form, it's going to be 3.13, right? Because I need to move the decimal from here until there's just one number that's not 0 in front of the decimal. One non-zero number in front of the decimal, everything else behind it doesn't matter, times 10. And what do we know about the exponent? If it's a small decimal number, that it's going to be a negative exponent. So it's times 10 to the negative what? Right? To get from here to behind the 3, how many do we need to move? We need to move 1, 2, 3. Don't stop there because you got to get behind the 3. We had to move 4 spaces. 1, 2, 3, 4 spaces. So it's going to be 3.13 times 10 to the negative 4. Not negative 3, even though you counted the 3 zeros. Count those 3 zeros and get behind the 3. That's a 4th. Okay? So 3.13 times 10 to the negative 4th. Check your answer. 3.13 times, not plus, times 10 to the negative 4th. No. All right. 0.00. No. Hoping it would do it for us. Maybe your calculator will. Number 7, again, this is a very small number, so it's going to be a negative exponent. I'm just going to get it set up. I'm going to go behind all the zeros until I get to my first non-zero digit. So I know it's going to be 6, and then the decimal point, 273 times 10, and I know it's going to be a negative, right? Now I need to count how many moves I had to make between that point and that point, right? How many numbers is it? We've got 1, 2, 3, 4. Those are the zeros, count the 6. We've got 5. Our answer is 6.273 times 10 to the negative 5th. We moved the decimal point 5 places, so that's how we know what our n is. We moved it 5 places, so it's negative 5 because it's a small number. 2,100,000, all right? 2,100,000 becomes 2.1, right? I'm going to ignore all those other zeros, times 10, because that's a big number. It's not going to be a negative exponent. And just how many, first of all, where is the decimal point? The decimal point is behind all of that. How many spaces did I have to move to get it between the 2 and the 1? My first space, Here's my second space. Here's my third space. I had to move it. So I went 1, 2, 3. Here's my fourth space. Here's my fifth space. So those are all the zeros, but I need to get in front of the 1 behind the 2. So there's actually 6 spaces. So it's 2.1 times 10 to the positive 6. It's positive 6 because it's 2 million. It's a really big number, okay? Number 9 is a word problem, but it's still just a computer compiles a program in 0.000827 seconds. What would that be in scientific notation? Instead of 0.0008, we're going to call that 8 because it's our first non-zero number. And then we're going to add our decimal point, 0.27 times 10. That's a really, really small number. So it's going to be a negative exponent. Small decimal numbers will have negative exponents. 8.27 times 10 to the negative. How many spaces did we have to move to get from here to here? 1, 2, 3, 4, right? 8.27 times 10 to the negative 4. Next one. A light year is a measure of length defined as the distance that light travels in 1 year, which is about miles. Write this number in scientific notation. We know it's going to be 5.9, right? Times 10. It's a big number, so that's going to be a positive. It's not going to be a negative exponent. How many points, how many place values do I need to move between here and 5.9, right? So we're just going to count really, really carefully. I'm probably just going to cross them out as I count them. That's number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10, 11, 12. 5.9 times 10 to the 12. 671.667. Don't worry that that's a bunch of numbers to put behind the decimal point. We still just need one number in front of the decimal. So it's going to be 6.71667 times 10. Let's count them. 1, 2, 3. Oh, don't start from the back like I did. It's already right there. It's already right there. Good thing I did that example question. Let me change it color. So from here to here, 1, 2, 10 squared. Good. If it's to the right of the decimal, you can ignore it. Like I should have ignored it when I started counting in purple and had to restart counting in blue. Ignore that 0.5, right? We need it to equal 5.185 times 10. That's a big number, large number, so it's going to have a positive exponent. How many spaces do we have to move this to get it to between the 5 and the 1? 1, 2. So 518.5 is equal to 5.185 times 10 squared. Let's put that into Desmos because those numbers are small, so I think it'll like it. 518.5, and then we have 5.185 times 10 to the second power. What is 10 to the second power? 10 to the second power. That took way too long to just tell you it's 100, right? So we're just taking 5.185 and multiplying it by 100. 5.185 times 100. It's 518.5. Write the number as a decimal instead of as a number in scientific notation. Again, more than welcome to use your calculator, okay? So you can just take your calculator, put in 6.91 times 10 to the fourth, see what happens. 6.91 times 10 to the fourth. If you're taking chemistry, this is really important. I know it seems tedious and like, what are we doing? But this will come up a lot in your chemistry class. So if you are already fluent, it's going to really help you, okay? So 6.91 times 10 to the fourth is 69,100 because 10 to the fourth is 10,000. Why? Because it's just 10 times itself 4 times. So you're saying 6.91 times 10, 4 times. And we get that, all right? Remember, if that number is positive, it's going to be a big number. If the decimal is positive, bigger than 1. If that number is negative, that number is going to become smaller, or a decimal, okay? Like 1.16 times 10 to the negative fourth. I don't think our calculator will do anything other than scientific notation when you get past -3, but yours might. Welcome to use it. Here's the long way to do it. 1.16, 10 to the negative fourth. So I know I need to move it 4 times, right? 1, 2, 3, 4. Which way should I move it? Should I move it that way, make the number bigger? Or should I move it that way and make the number smaller? So if I move the decimal this way, that'll be a big number. If I move the decimal that way, it'll make it small, right? Here, we moved it from here, we moved it that way and we made the number bigger because it was positive. All right, so because that's negative, we're gonna move it this way and we're gonna make it smaller. So instead of 116, and the decimal used to be right there, right? We need to move it that way to make it smaller because it's a negative, and we need to move it 4 times. 1, 2, 3, 4. So it started here. I'm just going to move it 1, 2, 3, 4 times. Okay. 1.16. The decimal started here, but we're moving it backwards because it's a negative. Filling those in with zeros. Okay. 1, 2, 3, 4. And then the decimal point. So we would even put a decimal point before it. That makes sense? So when it's a negative, we're going to move the decimal point this way. When it's a positive, we're going to move a decimal point that way. Feel free to use your calculator to help, okay? So that becomes 0.000116. Don't leave any of that off, okay? Because we did say ignore to the right of the decimal, but then add those digits in after converting the whole number to scientific notation. So you can't fully ignore it. You add it on to the end, okay? So 1.16 times 10 to the negative fourth is 0.000116. All right, again, we have 5.705 times 10 to the negative 6. Again, a small number because that's a negative sign. So we're going to go backwards. We have 5.705. It started here, and we need to go back 6, right? It was there. We're going to go back 1, 2, 3, 4, 5, 6. We're going to end here after the 6th move, all right? So that's those 6 exponential values covered. Put it right there. So those all become zeros. And don't forget that you need a zero in front of a decimal point. So 5.705 times 10 to the negative 6 becomes 0.000005,705. Rewrite it. 0.000005,705. Oh, okay, maybe our calculator will show this a certain way. What if I just type in all those zeros? 0.00005705. No. Okay. Now we have 5.587 times 10 to the 6th. That is a positive exponent, so it's a big number. Big numbers are going to move that way. Big is that way, big is that way. These last two were small. Good. Big because it's positive. So 5.587 becomes 5.587. Again, we were starting right here, and we're going to move it 6 places. So this is 1, 2, 3, 4, 5, 6. And we're going to end right there. After the 6th, we're going to fill in the missing zeros. So that just becomes and you don't need to put that decimal, right? 5,587,000,000. No, 5,587,000. Okay. Now, there are 2.599 times 10 to the 4th miles of highway, roads, and streets in a certain state. How many is that? 2.599. We're going to make it bigger because it's positive. We'll move it 4 places. It was right here. We're going to move it 1, 2, 3, and we need one more. We'll move it past that. We'll just tack on a 0. So how many miles of highways, roads, and streets? That is 25,990 miles. Again, put that into your calculator, 2.599 times 10 to the 4th. You should get 25,990. Okay, here, evaluate the expression using exponent rules, write the rules in scientific notation. I would just jump straight to Desmos, okay? So we see that we are multiplying 2 times 10 squared times 7 times 10 cubed, right? Put that exactly into Desmos as it is. What we have is 2 times 10 squared times 7 times 10 to the 3rd. Oops. And it will give you your answer as 1400000. And you can put that answer into scientific notation. So if you had this number, $1,400,000, let me make sure that's what was in my calculator. Yeah, looks like it. And you had to put that back into scientific notation, right? What would you do? You would say, well, that's going to be equal to 1.4 times 10. Is my exponent going to be positive or negative? It's going to be positive because that's a big number. And how many spaces did I have to move between 1.4 and 1,400,000? I had to move it 1, 2, 3, 4, 5, 6 spaces. So that's 1.4 times 10 to the positive 6. 1.4 times 10 to the 6th. Same answer. Good? Oh my goodness. Stop share. Now, if you want to do it without your calculator, when performing operations with scientific notation, there are 3 approaches. Use arithmetic rules, or just like the math rules that you know, on the decimal numbers part, and rules of exponents on the 10 to the power of parts, and then convert the answer into proper scientific notation, as we did here after we just used a calculator. Good? Option 2, you can convert that number to standard form, right? 2 times 10 squared is just going to be 200. And then 7 times 10 cubed is going to be 7,000. 7,000 times 200 is 1,400,000, right? So it was 2 times 10 squared is 200. 7 times 10 cubed is 7,000. 7,000 times 200 is that same answer we got. So you're welcome to do it like that. That's option 2. So you take it from scientific notation back into standard form. So that was 200 times 7,000 is 1,400,000. And then we put it back into scientific notation down there, which is 1.4 times 10 to the 6th. Or do all calculations directly with a calculator. We did that, right? Option 1, use arithmetic rules on the decimal parts and rules of exponents on the x to the 10 parts, right? So if we did that here, arithmetic rules on the decimal numbers parts. The decimal number parts were the 2 and the 7. So for the 2 and the 7, they are being multiplied. 2 times 7 is 14. And then the rules of exponents parts says we had a 10 squared times 10 to the 3rd equals, what's the rule of exponents say? We add those together. 10 to the power of 2 plus 3 is 5, right? So that becomes, 2 times 3. Right, rules of exponents is you have to multiply them. We add them. 10 to the, I panicked there. I apologize. I wanted it to immediately match this one. Ignore my panic. Arithmetic says 2 times 7 is 14. 10 squared times 10 to the 3rd is 10 to the 5th. I panicked and said 6 because I wanted it to match that. Ignore that. So now we have 14 times, right? 10, not to the 6th, but to the 5th. And why did we have that answer? Because this is not scientific notation. Why isn't this scientific notation? Because you can only have, remember our rule? One number before the decimal. Where's the decimal in the number 14? The decimal is right here. We need to move it over 1, right? 14 times 10 to the 5th is the same as 1.4 times 10 to the 6th. Because we had to move it over 1 more. Or 1.4 times 10 to the 1st times 10 to the 5th, right? So that 5th is for the 14. The 1 is to change the 14 to the 1.4 and add it to the 5. So 14 times 10 to the 5th, but we have to put that into scientific notation and say 1.4 times 10 to the 6th. So those are the 3 options. Option 1, the one we just did, is the most mathematical, but most messy, as you can see by me messing up, right? And then explaining it like that, and then explaining it like that. It's a little bit messier. Option 2 is straightforward. We converted them to 207,000 and reinforces how scientific notation works. Option 3, if You trust your calculator, you know how to enter everything in, it gets the job done, right? Okay, so when we have 6.7 times 10 to the negative 2 times 6.2 times 10 to the positive 2, the mathy way to do it, right? The mathy way to do it was take 6.7 and multiply it by 6.2. 6.7 times 6.2 is 41.54. And then we've got 10 to the negative 2 times 10 to the positive 2 is, and you add those together, right? The rule of exponents says we add the exponents if the base is the same. So that's 10 to the power of negative 2 plus 2, which is 10 to the power of 0. What's 10 to the power of 0? It's 1, right? Anything to the power of 0 is 1. Good. So now we have, as our mathy answer, well, almost there, 41.54 times 1, which is just 41.54, because we took the purple, 6.7 times 6.2, and we took the yellow, 10 to the negative 2 times 10 to the 2, got 1. 41.54 times 1 is 41.54. It's almost in scientific notation. What's wrong? There are 2 numbers in front of the decimal, so we're going to move it 1, right? Because it's a big number, the exponent is going to be positive. So 41.54 is actually 4.154 times 10 to the power of 1, or just 10. Good? Let's see if, when we put that into our calculator, we get the same thing. So it was 6.7. Ooh, I backspaced too far and then I don't look up at my screen. 6.7 times 10 to the power of negative 2. Again, just make sure you're being really careful with entering it correctly. Times, with parentheses, you don't need to put the multiplication symbol between the parentheses. It's implied. 6.2 times 10 squared. And we get 41.54, which we converted to 4.154 times 10. 4.154 times 10, or 4.154 times 10 to the power of 1. Good? So that was the math way, reinforced by the calculator way. But you're welcome to just do these on your calculator. I'm going to show you how to do the fraction style on the Desmos calculator. So we have 8 times 10 to the 4th divided by 4 times 10 to the 8th. Okay, look at the mathy way, right? The mathy way is going to say 8 divided by 4 is 2. We agree, right? 10 to the 4th divided by 10 to the 8th means we subtract them, right? Is 10 to the negative 4th. So our math answer is 2 times 10 to the negative 4th. 8 divided by 4 is 2. The quotient rule of exponents is if the base is the same and they're being divided, you take, let me explain that a little better. This is because we have 10 to the 4th divided by 10 to the 8th. Those are the same base. So we take that exponent and we subtract from the top exponent, we subtract the bottom exponent. And we got 10 to the negative 4th because 8 minus 4 is a negative 4. Good. If we put that into our calculator, will we get 2 times 10 to the negative 4th? Be really careful. 8 times 10 to the 4th divided by 4 times 10 to the 8th, 2 times 10 to the negative 4th. That's the number we got. doing it the mathy way, right? 4 times 10 to the negative second divided by 8 times 10 to the fourth. 4 divided by 8 is not as beautiful as 2. 4 divided by 8 just simplifies to 1/2. So we have 1/2, or what is 1/2 as a decimal? 0.5. So we have 0.5 for the integer part. And then for 10 to the negative 2 divided by 10 to the fourth, that becomes 10 to the power of negative 2 minus 4, which is 10 to the negative 6, right? So what I'll have is 0.5 times 10 to the negative 6. Ignore that extra decimal point, right? But this isn't done because we have to adjust this into scientific notation. There's no number in front of the decimal, so it's not in scientific notation. It has to be one non-zero number in front of the decimal. You put this in front of the decimal, but that's not a non-zero number. So let's move it from a small number, make it bigger. So now it's 5 because I moved it 1 times 10. Which way did I move it? I moved it that way, so that's a negative. So that's a negative 1. So for 0.5 is the same as 5 times 10 to the negative first. Let's confirm. 5 times 10 to the negative 1 is 0.5, right? We moved it to the right, so that's a negative decimal place. And then we have that times 10 to the negative 6. How do we combine these now? How do we combine this? We are multiplying bases, the same base with exponents, so we add them, right? 10 to the power of negative 1 plus negative 6. 5 times 10 to the negative 7. Let's see if that's what we get when we divide it with our calculator. 4 times 10 . Or talk to myself. 5 times 10 to the negative 7. That's what we got. Good. Here, we can multiply 5 times 7 is 35. And then, what would we do for that? 10 to the negative third times 10 to the negative 2. 10 to the negative 3 minus 2, right? Because you add them. That's the rule of exponents. That becomes 35 times 10 to the negative 5th. But that's not an exponential form yet. It needs to switch to 3.5. 3.5, we made it smaller. So that's a positive exponent, right? 35 is 3.5 times 10. Right? 3.5 times 10 becomes 35. So probably this last conversion and recombining it with the original second half of the scientific notation is probably the most confusing part, the easiest spot to make a mistake. So that's finally 3.5 times 10 to the negative 4th, right? Because negative 5 and 1 will make negative 4. Feel free to check your answer in Desmos. Here we have 2.7 times 10 squared. All right, here we have decimals in fractions. So 2.7 times 10 squared divided by 0.9 times 10 to the negative 4th. Welcome to put it into Desmos. If not, you would take, right, let's keep the color scheme the same. 2.7 divided by 0.9 or 0.9. What do you think that number gets smaller or bigger? 2.7 divided by 0.9 is 3. Good. So that's, sorry, so that is that half. That becomes 3. And then we've got 10 squared divided by 10 to the negative fourth. And that rule is if the base is the same and it's being divided, you just subtract. So 10 to the power of 2 minus a negative 4. And what happens when we minus a negative? It becomes a positive, right? 10 to the power of 2 plus 4, which is 10 to the power of 6. So our answer will be 3 times 10 to the 6th. Here, your numbers are pretty big, so I wouldn't convert these out of scientific notation to multiply them to convert them back into scientific notation. I wouldn't do the middle option. 5 times 6 is 30. 10 to the negative 30 times 10 to the negative 25th. Sorry, 10 to the power of negative 30 times 10 to the power of negative 25. Again, when the bases are the same, you can add those exponents together, so that becomes 10 to the power of negative 30 plus negative 25, which is just negative 30 times minus, sorry. If I try to write and talk at the same time and I'm not writing and talking about the same thing, it comes wrong. That's supposed to be multiplication. Supposed to be. You do. So negative 30 minus 25, you're combining two negatives, right? So that's 30, 40, 55. So that becomes 30 times 10 to the negative 55, but, right, 30 still needs to be put in exponent form, or sorry, in scientific notation. 30 becomes 3 times 10, right? And it's a positive 10. 30 is 3 times 10. It wouldn't be 3 times 10 to the negative 1, it would be positive 1. 30 equals 3 times 10 to the positive 1 times 10 to the negative 55th. These are being multiplied, that's a positive 1, right? And a negative 55. So we add them, 1 minus 55 is negative 54. So our final answer is 3 times 10 to the negative 54. Good? Here we have 5.6 times 10 to the 15th times 4.3 times 10 to the 24th. 5.6 times 4.3 is 5.6 times 4.3 is 24.08. What happens if we do 10 to the power of 15 times 10 to the power, oops, not 20, 10 to the power of 24. It's 10 to the power of 39. So 10 to the power of 15 times 10 to the power of 24 is 10 to the power of 39. Sorry, down here. How did we get that? Because we added 15 and 24 becomes 39, right? Those halves together, 24.08 times 10 to the 39th. Again, we're not done because we don't want 24, we want 2.4. 408 times, we moved it that way, right? It was a big number, we've made it smaller, so that's going to be a positive exponent. Now we need to combine these two, 10 to the first power and 10 to the 39th power, and we get 2.408 times 10 to the 40th. All right, guys, those are all the scientific notation examples I have, and I hope that that was clear. Please just shoot me an email if it was not. Have a good day.